Tonight, we're going to explore one of the most extraordinary contradictions in the universe. In the constellation Taurus, roughly 6,500 light years from Earth, a nebula has been glowing for nearly 1,000 years. The star that created it is dead. It exploded. It tore itself apart in one of the most violent events nature can produce, yet something at the center of the wreckage is still alive. Not a star, not a flame. A city-sized object spinning 30 times every single second, generating more power than our sun, flooding the surrounding gas with energy so intense that the entire nebula shines across every wavelength of light we can detect. A dead star is powering a living nebula, and how it does this is one of the most remarkable stories in all of astrophysics. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with something that, on the surface, doesn't seem to make sense. If you took a massive star, one many times heavier than our sun, and watched it reach the end of its life, you would expect one outcome: destruction. Total, absolute destruction. The star exhausts its fuel, its core collapses, the outer layers crash inward and rebound outward in a catastrophic explosion that, for a few weeks, can outshine an entire galaxy of hundreds of billions of stars. A supernova. One of the most violent events the universe regularly produces. After that, you would expect silence, darkness, perhaps a cloud of expanding debris, glowing faintly for a time as it cools, gradually thinning and dimming until it merges with the emptiness between the stars. The star is gone. The explosion is over. Whatever energy was released during that detonation should slowly dissipate, stretching thinner and fainter over the centuries until eventually there is nothing left to see. That should be the end of the story. But in the constellation Taurus, the story did not end. Something survived the explosion, and that something is not sitting quietly in the wreckage. It is actively, relentlessly pouring energy into the surrounding debris, keeping it bright, keeping it hot, reshaping it in ways astronomers can observe from one year to the next. The nebula around it is not fading the way it should. It's glowing fiercely across the entire electromagnetic spectrum, from radio waves to visible light, to X-rays to some of the highest energy gamma rays ever detected from any cosmic source. The object responsible for all of this is smaller than most cities on Earth. It measures roughly 20 kilometers across, about 12 miles. You could drive across it in 15 minutes if there were a road. And yet this tiny remnant, this impossibly compressed leftover from a star that destroyed itself nearly 1,000 years ago, produces more energy every single second than our sun does in the same interval of time. It has been doing this continuously since the original explosion, and it will keep doing it for thousands of years to come before it even begins to noticeably weaken. This is the Crab Nebula, and the Crab pulsar at its center. Their story begins with a light that appeared in the sky almost a millennium ago. In the year 1054, astronomers in China noticed something unusual in the heavens. A brilliant new point of light had appeared, where none had been before, sitting near the star we now call Zeta Tauri, in the constellation Taurus. Court astronomers serving the Song dynasty recorded it carefully, calling it a guest star, the term they used for celestial objects that appeared temporarily in positions where no star normally existed. This guest star was extraordinary. It was so bright that it was visible during the daytime, For roughly 23 days, observers could look up at the sky in broad daylight and see this object shining alongside the sun. Not as bright as the sun, certainly, but clearly visible against the blue sky. A point of light that had no business being there in the middle of the day. At night, it was even more spectacular. It outshone everything in the sky except the moon. Japanese astronomers recorded the same event. There are possible references in Arabic records as well. Across the world, people looked up and witnessed what was, in the most literal sense, a once-in-a-civilization event. The guest star remained visible to the naked eye for roughly 2 years before finally fading from view. Then, as far as anyone could tell, it was gone. For centuries, no one connected that ancient sighting to anything still visible in the modern sky. It was not until 1731 that the English physician and amateur astronomer John Bevis pointed a telescope at the constellation Taurus and found a faint, fuzzy patch of light near the spot where Chinese astronomers had recorded their guest star nearly 700 years earlier. 27 years later, in 1758, the French astronomer Charles Messier independently observed the same nebulous object and catalogued it as the first entry in his famous list of nebulae and star clusters. It became M1, the very first Messier object. Then, in 1848, the Irish astronomer William Parsons, also known as Lord Rosse, observed M1 through what was then the largest telescope in the world, a massive reflector with a mirror 6 feet across. His drawing of the nebula showed filamentary structures that he thought resembled the legs of a crab. The name stuck. The Crab Nebula. But what exactly was it? For decades, astronomers debated the nebula's nature. Some believed it was simply a cloud of glowing gas. Others suspected a connection to the guest star of 1054. That connection became definitive in the early 20th century when astronomers measured the nebula's expansion. By comparing photographs taken years apart, they could see that the nebula was growing larger. Tracing that expansion backward in time, they calculated that all the material must have originated from a single point roughly 900 years earlier. The timing matched. The Crab Nebula was the remnant of the explosion that Chinese astronomers had witnessed in 1054. The guest star had been a supernova, a dying star's final cataclysm, and the Crab Nebula was the expanding cloud of debris it had left behind. But this raised a problem. Supernova remnants are supposed to fade. They expand, they cool, they thin out, and they gradually become dimmer as the original energy of the explosion spreads over an ever-increasing volume of space. This process typically unfolds over a few tens of thousands of years, after which the remnant merges into the surrounding interstellar medium and disappears. The Crab Nebula was not doing that. It was far too bright for its age, far too energetic. Something was feeding it, pumping energy into it, keeping it lit up like a lantern nearly 1,000 years after the explosion that created it. To understand what that something is, we need to look at what happens when a massive star dies. Because the key to the Crab Nebula's impossible brightness lies not in the explosion itself, but in what the explosion left behind. Stars spend their lives in a constant battle between two opposing forces. On one side is gravity, relentlessly pulling everything inward, trying to crush the star down into the smallest possible space. On the other side is the outward pressure generated by nuclear fusion in the star's core, which pushes back against gravity and holds the star up. For most of a star's life, these two forces are balanced. The star is stable. Hydrogen atoms in the core fuse into helium, releasing enormous amounts of energy. This energy creates the heat and radiation pressure that counteract gravity. As long as there is fuel to burn, the star holds together. A star like our Sun will burn hydrogen in its core for about 10 billion years. It is a modest star, not particularly massive, and it burns its fuel slowly and steadily. But a massive star, one with 8 or 10 or 20 times the mass of our Sun, burns through its fuel far more rapidly. The more massive the star, the hotter its core, and the faster the fusion reactions proceed. A star 20 times the mass of our Sun might exhaust its hydrogen in just a few million years, 1,000th of the Sun's lifetime. When a massive star runs out of hydrogen in its core, it does not simply stop. Instead, the core contracts under gravity, heats up, and begins fusing helium into heavier elements: carbon, oxygen. When the helium is exhausted, the core contracts again, heats up further, and fuses carbon into neon and magnesium. Then neon into oxygen. Then oxygen into silicon and sulfur. Each successive stage burns faster than the one before it. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning might persist for roughly 1,000 years. Neon burning lasts perhaps a single year. Oxygen burning continues for a few months. And silicon burning, the final stage, lasts roughly 1 day. 1 single day. During that last furious day of silicon fusion, the core is producing iron. And iron is where everything changes. Iron is the end of the road for nuclear fusion. Every element lighter than iron releases energy when its atoms are fused together. That released energy is what powers the star, what creates the pressure that holds it up against gravity. But iron does not release energy when fused. Fusing iron into heavier elements actually absorbs energy rather than releasing it. It is an energy sink, not an energy source. So when the core fills with iron, there is nothing left to burn. No fuel, no energy source, no outward pressure to fight gravity. And gravity has been waiting for this moment for millions of years. The iron core at this stage is roughly the size of Earth, perhaps 10,000 to 15,000 kilometers across, and it contains about 1.5 times the mass of our Sun. All of that mass compressed into a volume comparable to our own planet. Without the outward push of fusion energy, gravity takes over completely. The core collapses, and it collapses fast, catastrophically fast. The inner core plunges inward at speeds approaching 70,000 kilometers per second, roughly a quarter of the speed of light. In less than a single second, the entire core, this Earth-sized ball of iron that took millions of years to build through successive rounds of nuclear fusion, is crushed down to an object roughly 20 kilometers across. Consider the magnitude of that collapse. An object comparable in size to Earth, about 12,700 kilometers in diameter, crushed in less than 1 second down to something 20 kilometers across. That is a shrinkage factor of more than 600 in diameter. The density increase is beyond description. Matter that was already extraordinarily dense becomes something that has no analog in everyday experience. The collapse holds only when the matter reaches nuclear density, the density of an atomic nucleus. At this point, the protons and electrons in the iron atoms are forced together so violently that they merge, converting into neutrons and releasing a colossal flood of nearly massless particles called neutrinos. The core becomes a ball of neutrons, packed so tightly they are essentially touching. resisting any further compression through a quantum mechanical force called neutron degeneracy pressure. This is a neutron star, the densest stable form of matter known to exist in the universe. Meanwhile, the outer layers of the star, which have been falling inward during the core collapse, slam into this suddenly rigid neutron core and bounce. The bounce, reinforced by heating from the intense neutrino flood, drives a shockwave outward through the rest of the star. That shockwave tears the star apart. The outer layers are blasted into space at speeds of thousands of kilometers per second. This is the supernova explosion, and it is spectacularly energetic. For a few weeks, a single dying star can release more energy than our sun will produce over its entire 10 billion year lifetime. It becomes the brightest object in its entire cosmic neighborhood, but the core remains, crushed, transformed, barely recognizable as anything that was once part of a star. No longer burning fuel, no fusion reactions, no fire of any kind, just an unimaginably dense ball of neutrons, roughly 20 kilometers across, containing about 1.5 times the mass of our sun. This is what was left behind when the guest star of 1054 exploded. This is what sits at the center of the Crab Nebula today. A neutron star. And a neutron star is one of the most extreme objects in the known universe. To call it dense barely scratches the surface of what it actually is. A typical neutron star packs roughly 1.5 solar masses into a sphere about 20 kilometers in diameter. That gives it a density of around 1 billion tons per teaspoon. If you could somehow scoop up a teaspoonful of neutron star material and bring it to Earth's surface, it would weigh about as much as a mountain. A sugar cube of this material would outweigh every building in a large city combined. The surface gravity is equally staggering. The gravitational pull at the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel right now standing on Earth. An object dropped from a height of 1 meter above the surface would impact at roughly 7 million kilometers per hour. Light itself bends noticeably in this gravitational field. If you could somehow observe a neutron star from a safe distance nearby, you would actually see slightly around the back of it, because gravity curves the paths of photons traveling close to the surface. The interior is stranger still. Beneath a thin outer crust of crystallized iron and heavy nuclei, perhaps only 1 kilometer thick, lies a sea of neutrons so dense and compressed that they exist in a superfluid state, a quantum condition with zero viscosity, flowing without any friction at all. Deeper still, near the very center, conditions may become so extreme that neutrons themselves break apart into their constituent quarks, forming exotic states of matter that exist nowhere else in the observable universe. We are not entirely certain what happens in the innermost core of a neutron star, because the pressures and densities exceed anything we can recreate in any laboratory on Earth. But 2 properties of the neutron star matter more than all others for understanding the Crab Nebula: its rotation and its magnetic field. Because these 2 properties are what turn a dead, inert stellar corpse into one of the most powerful engines in the galaxy. When the core of a massive star collapses to form a neutron star, it does not just become smaller, it becomes dramatically faster. This happens because of a fundamental law of physics called conservation of angular momentum. Angular momentum is the rotational equivalent of linear momentum. Just as a moving object tends to keep moving unless a force stops it, a spinning object tends to keep spinning. And there is a crucial relationship between the size of the spinning object and how fast it spins. When a spinning object shrinks, it spins faster, not a little faster. The spin rate increases in proportion to the square of how much the radius decreases. You have seen this principle at work. Think of a figure skater performing a spin on the ice. When the skater stretches their arms wide, they rotate slowly. When they pull their arms tight against their body, they spin dramatically faster. Their angular momentum has not changed. What changed is the distribution of mass relative to the axis of rotation. By pulling mass closer to the center, the rotation rate has to increase to compensate. It is not a choice. Physics demands it. Now apply this same principle to the collapse of a stellar core. Before the collapse, the iron core of the massive star might be several thousand kilometers across, rotating perhaps once every few hours. Nothing particularly fast by everyday standards, just a slow, steady turn. Then the core collapses. It shrinks from thousands of kilometers in radius to just 10 kilometers. That is a contraction factor of several hundred. And because angular momentum must be conserved, the spin rate increases by the square of that factor, by tens of thousands or more. A core that was lazily rotating once every few hours suddenly spins dozens of times every single second. This is why the Crab pulsar rotates roughly 30 times per second. Not because some force is spinning it up after the fact. Not because some engine is driving the rotation. It spins that fast simply because the object that became it was once vastly larger and was spinning slowly, and when it collapsed, all of that rotational energy was compressed into a tiny volume. The spin had to increase. There was no alternative. 30 rotations per second. Think about what that means for an object this dense. Every single second, something roughly 20 kilometers across, containing 1.5 times the mass of our Sun, completes 30 full revolutions. A point on its equator moves at a significant fraction of the speed of light. The surface whips around so fast that if the neutron star were any less dense, the centrifugal forces would tear it apart. Only the immense gravity, 200 billion times what you feel on Earth, keeps it from flying to pieces. The same basic physics that amplifies the rotation also intensifies the magnetic field. Stars possess magnetic fields. Our Sun has one. It is not particularly strong by cosmic standards, but it exists. Generated by the motion of electrically conducting plasma in the Sun's interior. The cores of massive stars also carry magnetic fields, typically stronger than the Sun's. When the core collapses, the magnetic field gets compressed along with everything else. There is a principle called conservation of magnetic flux, which states that the total magnetic field threading through a given area is preserved during the collapse. When that area shrinks by a factor of tens of thousands, as it does when a stellar core becomes a neutron star, the strength of the magnetic field concentrated within that smaller area increases by the same enormous factor. The result is extraordinary. A magnetic field that was already substantial in the original stellar core becomes something almost incomprehensibly powerful in the neutron star. The Crab pulsar has a surface magnetic field estimated at hundreds of millions of Tesla. To put that in any kind of perspective, Earth's magnetic field is about 50 millionths of a Tesla. The Crab pulsar's field is about 8 trillion times stronger than Earth's. The strongest permanent magnets humans manufacture produce about 1 Tesla. The strongest magnetic fields ever briefly generated in a laboratory are about 1,200 Tesla, and even those exist for only tiny fractions of a second before the equipment is destroyed by the enormous forces involved. The Crab pulsar's field dwarfs anything human technology has ever produced, and it sustains this field permanently, without any external power source, the magnetic structure frozen into the neutron star's interior by the superconducting properties of matter at nuclear density. So now we have an object that is extraordinarily dense, spinning 30 times per second, and wrapped in one of the most powerful magnetic fields in the entire galaxy. This combination, rapid rotation plus intense magnetic field, is what transforms the neutron star from a dead remnant into a working engine. Because when you spin a powerful magnet at tremendous speed, things happen. Extraordinary things. The Crab pulsar's magnetic field is not perfectly aligned with its rotation axis. The magnetic axis, the imaginary line connecting the north and south magnetic poles, is tilted at an angle relative to the spin axis. This misalignment is crucial. As the neutron star spins, its magnetic field spins with it. And because the magnetic axis is tilted, the regions near the magnetic poles sweep through space, like the beams of a lighthouse. Near these poles, conditions are extreme enough to generate concentrated beams of radiation, beams of radio waves, visible light, X-rays, and other forms of electromagnetic energy, all focused into narrow cones that rotate with the star. From Earth, we see the result as pulses. Every time one of those beams sweeps across our line of sight, we detect a brief flash of radiation. Then the beam rotates away, and we see nothing until the next sweep brings it around again. The result is a regular, repeating signal, a pulse arriving roughly 30 times every second with clockwork precision. This pulsing behavior is why these objects are called pulsars, pulsating stars. Though the name is slightly misleading because the star is not actually pulsating, not expanding and contracting, it is spinning, and we are seeing a rotating beam sweep past us, exactly like a lighthouse beam sweeping across a dark coastline. This lighthouse model of pulsars was one of the great explanatory triumphs of 20th century astrophysics. It elegantly explained a phenomenon that, when first detected, was so strange and so precisely regular that some astronomers briefly wondered whether they had stumbled upon signals from an extraterrestrial civilization. That discovery came in 1967 at Cambridge University in England. A graduate student named Jocelyn Bell Burnell was analysing data from a new radio telescope that she had helped construct. The telescope was designed to study interplanetary scintillation, the twinkling of distant radio sources caused by the solar wind. But buried in the data, Bell Burnell noticed something unexpected. A signal that appeared as a regular, repeating pulse, arriving once every 1 1/3 seconds with extraordinary precision. The regularity was astonishing. Natural sources of radio emission, things like galaxies and gas clouds, produce signals that fluctuate randomly. They do not pulse with the precision of a metronome. For a brief time, the research team genuinely considered the possibility that the signal might be artificial, a beacon from another civilization. They even gave the source a half-joking designation, LGM1, standing for Little Green Men 1. But then Bell Burnell found a second pulsing source in a completely different part of the sky, with a different pulse period. Then a third, then a fourth. Whatever these objects were, they were not alien beacons. They were a natural phenomenon, something the universe produced on its own. The explanation came quickly. Within months, theorists proposed that the signals were coming from rapidly rotating neutron stars, objects that had been predicted decades earlier on theoretical grounds, but never directly observed. The first pulsar, CP 1919, had a relatively leisurely pulse rate of about once every 1 1/3 seconds. But soon, astronomers began finding pulsars spinning much faster. In 1968, just a year after Bell Burnell's initial discovery, a pulsar was found at the very center of the Crab Nebula. And this one was spinning fast, roughly 30 times per second. 30 pulsars arriving every single second with a precision that rivaled the best atomic clocks on Earth. This discovery was transformative. It confirmed that the Crab Nebula harbored a neutron star. It proved that neutron stars could rotate at extraordinary speeds. And most importantly, it immediately suggested where the Crab Nebula had been getting its energy all along. Because the Crab pulsar is not simply sitting inside the nebula and passively sweeping lighthouse beams across the sky. It is actively pumping energy into its surroundings. The lighthouse beams are just the most visible symptom of a much larger and more powerful process. The real action is happening in the space immediately around the pulsar, where the spinning magnetic field generates electric fields of almost unimaginable strength, accelerating particles to nearly the speed of light and driving a relentless wind of matter and energy outward into the nebula. The supernova explosion that created the Crab Nebula ended nearly 1,000 years ago. The shockwave from that detonation has long since passed through the surrounding gas and raced far ahead. Yet the nebula continues to glow, fiercely and brilliantly, because the engine at its center never stopped running. The star is dead. It will never burn fuel again. It will never ignite another fusion reaction. But its corpse is still at work, converting the energy of its own rotation into the power that keeps an entire nebula alive. And understanding exactly how it does this, how a spinning ball of neutrons smaller than a city can illuminate a cloud of gas 11 light years across, requires us to look much more closely at what is happening in the extraordinary space immediately surrounding the pulsar. Because the mechanism that connects a spinning dead star to a glowing nebula is one of the most elegant and powerful processes in all of astrophysics. So now we arrive at the central question, the one that puzzled astronomers for decades before the answer finally emerged. Where's the energy coming from? The star is dead. Let me be absolutely clear about that. The original star, the one that shone in the sky of Earth nearly 1,000 years ago, is gone. It destroyed itself. The nuclear fusion reactions that powered it for millions of years have ended permanently. There is no fire burning inside the neutron star at the center of the Crab Nebula. No hydrogen fusing into helium. No helium fusing into carbon. No chain of reactions climbing the periodic table toward iron. All of that ended the moment the core collapsed. The neutron star is not generating energy through any kind of nuclear process. It is not a star in the traditional sense at all. It is a stellar corpse. The furnace has gone out and it will never reignite. And it is not feeding on anything from the outside either. Some of the most powerful objects in the universe, things like active galactic nuclei and certain X-ray binary systems, get their energy from accretion, from matter falling onto a compact object and releasing gravitational potential energy as it spirals inward. But the Crab pulsar is not doing this. There is no disk of infalling material spiraling around it. There is no companion star feeding it gas. It sits alone at the center of its expanding cloud of debris, surrounded by thin wisps of gas that are moving away from it, not toward it. Nothing is falling in. The neutron star is isolated. Whatever is powering the Crab Nebula, accretion is not the explanation. So if the energy is not coming from fusion, and it is not coming from accretion, and it is not coming from the original explosion that happened nearly 1,000 years ago, what is left? What possible source of energy could sustain a nebula this bright for this long? The answer is the rotation itself. The Crab pulsar is spinning roughly 30 times every second. And because it is extraordinarily massive for its size, roughly 1.5 times the mass of our Sun, compressed into a sphere only 20 kilometers across, that rotation represents an almost inconceivable amount of stored energy. Rotational kinetic energy. The energy of motion, specifically rotational motion, locked up in the spin of the neutron star. Think about it this way. When you spin a top on a table, the top has kinetic energy stored in its rotation. A heavier top spinning at the same rate stores more energy. A faster spinning top also stores more energy. The amount of rotational kinetic energy depends on both the mass of the spinning object and the speed of its spin. Double the spin rate and the stored energy does not merely double, it quadruples. Rotational energy scales with the square of the spin rate. This means that a small increase in how fast something spins produces a large increase in how much energy it carries. Now apply that same principle to the Crab pulsar. The mass is staggering, roughly 1.5 times the mass of our Sun, which is roughly 300,000 times the mass of Earth. And the spin rate is extraordinary, 30 complete revolutions every single second. A point on the equator of this neutron star whips around at a significant fraction of the speed of light. The combination of extreme mass and extreme spin rate produces a reservoir of rotational energy that is almost impossible to overstate. The total rotational kinetic energy stored in the Crab pulsar is estimated at roughly 2 × 10 to the 42nd joules. Writing that number out in full would require a 2 followed by 42 zeros. To make that more tangible, it is approximately equivalent to the total energy our Sun will radiate over the course of about 200 million years. All of that energy is sitting right there, locked up in the spin of something 20 kilometers across, something smaller than many cities on Earth. This is the fuel tank. Not fusion fuel, not gravitational potential energy. Rotational kinetic energy, pure and simple. The spin of the neutron star is its power source, and every second, a fraction of that stored rotational energy is being extracted and converted into the energy that powers the surrounding nebula. The tank is enormous, but it is being drained steadily, one revolution at a time, as the pulsar gradually slows down. Imagine a flywheel in a factory, a massive spinning disk that stores energy and releases it slowly to drive machinery. The Crab pulsar is the universe's version of that flywheel, except the flywheel is made of nuclear matter, weighs more than our Sun, spins 30 times a second, and drives not a machine, but an entire nebula across 11 light years of space. But how? How do you extract energy from a spinning object in the vacuum of space? How do you convert the rotation of a solid ball of neutrons into radiation and particles that can keep a vast cloud of gas glowing across every wavelength of light? The answer lies in the magnetic field. Because the Crab pulsar does not just spin, it spins while wrapped in one of the most powerful magnetic fields in the galaxy. And when you combine rapid rotation with an intense magnetic field, something extraordinary happens. You generate electric fields. This is a principle that Michael Faraday discovered in the 1830s, and it underlies virtually all of modern electrical technology. When a magnetic field changes relative to its surroundings, or when a conductor moves through a magnetic field, an electric field is induced. This is how generators work. You rotate a magnet near a coil of wire, and the changing magnetic field pushes electrons through the wire, creating an electric current. Every power plant on Earth, whether it burns coal, splits atoms, or captures the force of wind and water, ultimately works by spinning a magnet inside a conducting structure to generate electricity. It is one of the most fundamental relationships in all of physics. Change a magnetic field, and an electric field appears. A neutron star does something fundamentally similar, except on a scale that makes every power plant ever built by humanity look utterly insignificant. The neutron star is the magnet. Its rapid rotation provides the changing magnetic field, and the space around the neutron star, threaded by magnetic field lines and populated by charged particles, responds to that changing field by developing enormous electric potentials. As the Crab pulsar spins, its magnetic field sweeps through the surrounding space. Because the magnetic axis is tilted relative to the rotation axis, the field configuration is constantly changing from the perspective of any fixed point near the star. This changing, rotating magnetic field induces electric fields of almost incomprehensible strength. The voltages involved are beyond anything that exists on Earth or in any technology humans have ever constructed. The electric potential difference generated across the Crab pulsar's magnetic field reaches roughly 10 million billion volts. Let me put that in perspective. The most powerful particle accelerator on Earth, the Large Hadron Collider near Geneva, accelerates protons to energies equivalent to about 7 trillion volts. The Crab pulsar generates voltages more than 1,000 times larger. A single lightning bolt involves about 300 million volts. The Crab pulsar's electric field is more than 30 million times stronger than a lightning bolt. This tiny dead star is, in a very real sense, the most powerful particle accelerator in this entire region of the galaxy, and it operates continuously without any external power source, driven by nothing more than its own rotation and its own magnetic field. These electric fields are so intense that they can rip charged particles right off the surface of the neutron star. The surface of a neutron star is not like the surface of a planet. It is a crystalline lattice of iron nuclei and free electrons, compressed to extraordinary densities by the immense gravity. Under normal circumstances, that gravity, 200 billion times stronger than Earth's, would hold everything firmly in place. Nothing should escape. But the electric fields generated by the spinning magnetic field are powerful enough to overcome even this monstrous gravitational pull, tearing electrons and ions away from the surface and launching them into the space above. The result is that the neutron star does not sit in a vacuum. It cannot. The physics will not allow it. Instead, it is surrounded by a region of charged particles and magnetic field lines that rotate along with the star. This region is called the magnetosphere. The magnetosphere is filled with plasma, a mix of electrically charged particles threaded through and bound to the powerful magnetic field. This plasma does not float around the neutron star randomly. It is locked to the magnetic field lines, forced to spin with them, co-rotating with the star at exactly the same rate. Near the neutron star, the magnetosphere behaves as if it were a rigid extension of the star itself. An envelope of magnetic field and plasma all whipping around 30 times every single second. Picture it as a vast invisible structure anchored to the spinning neutron star. The magnetic field lines extend outward from the surface like the ribs of an umbrella, curving from one magnetic pole to the other. Charged particles are trapped on these field lines, spiraling along them, unable to move freely across them. The entire structure rotates as a unit, a corrotating magnetosphere that extends thousands of kilometers into space around a neutron star only 20 kilometers across. But this corrotation cannot extend outward forever, and the reason is one of the most elegant constraints in all of physics. Consider what happens as you move farther from the rotation axis. The magnetic field lines extending outward from the neutron star carry the corrotating plasma with them. Close to the star, those field lines are moving at manageable speeds. But farther out, the field lines must sweep through a larger circle in the same amount of time, which means they must move faster. This is the same reason the tip of a spinning propeller blade moves faster than the hub. The outer edge travels a much longer path in each revolution, so it covers more distance in the same interval, which means a higher speed. As you move outward from the Crab pulsar, the speed required for corrotation keeps increasing. At some distance from the rotation axis, that required speed reaches the speed of light. This distance defines an imaginary boundary surrounding the pulsar called the light cylinder. The light cylinder is not a physical object. There is no wall, no barrier, no surface you could touch. It is simply the mathematical boundary at which the corrotating magnetic field lines would need to travel at the speed of light to keep pace with the star's rotation. For the Crab pulsar, spinning at roughly 30 revolutions per second, the light cylinder sits at a radius of about 1,600 kilometers from the rotation axis. That is roughly comparable to the radius of the moon. So picture the geometry. The neutron star is 20 kilometers across, sitting at the center. The light cylinder, this critical boundary, extends about 1,600 kilometers outward. And everything between the neutron star surface and the light cylinder is spinning as a single locked structure, corrotating 30 times per second. But nothing can exceed the speed of light. This is one of the most fundamental laws of physics, confirmed by over a century of experiments. So what happens to the magnetic field lines that extend far enough from the pulsar that they would need to exceed light speed to keep corrotating? They cannot remain closed. They cannot curve back and connect from one magnetic pole to the other in a smooth loop, because closing that loop beyond the light cylinder would require parts of the field to move faster than light allows. Instead, those field lines are forced open. They break away from the closed corrotating structure and stream outward, spiraling away from the pulsar into the surrounding space, never returning. They become highways of energy flowing away from the neutron star. And this is the crucial piece, because these open field lines are the channels through which rotational energy escapes from the pulsar. Charged particles trapped on these open field lines are not confined. They are free to flow outward along the lines, accelerated by the enormous electric fields that exist along them, gaining energy with every meter they travel. By the time they reach the light cylinder and pass beyond it, they are moving at velocities indistinguishable from the speed of light. But where do all these particles come from? The neutron star's surface supplies some, torn free by the electric fields as I described. But the primary source of particles filling the Crab pulsar's magnetosphere is something far more exotic. the particles are created from energy itself, manufactured out of the vacuum through a process that blurs the boundary between radiation and matter. Near the pulsar's surface and in the regions above the magnetic poles, the electric and magnetic fields are so extreme that they trigger a phenomenon from the deepest level of fundamental physics. When a high-energy photon, a gamma-ray photon, passes through a sufficiently powerful magnetic field, it can spontaneously transform into a pair of particles, one electron and one positron. The positron is the antimatter counterpart of the electron, identical in mass and behavior, except that it carries a positive charge instead of a negative one. This process is called pair production, and it is one of the most direct demonstrations of Einstein's equivalence between mass and energy. Energy in the form of a photon goes in. Matter in the form of two real particles comes out. The energy is not destroyed. It is transformed into mass, into the substance of new particles that now exist in the magnetosphere, where nothing existed a moment before. The trigger for this cascade is elegant. The initial seed photons come from particles that were already accelerated by the electric fields. As these fast-moving particles race along curved magnetic field lines at nearly the speed of light, the curvature of their path forces them to radiate energy. This process, called curvature radiation, produces photons. Some of these photons carry enough energy to interact with the intense magnetic field and produce brand new electron-positron pairs. Those newly created particles are immediately seized by the same electric fields and accelerated to tremendous speeds. As they accelerate, they emit their own curvature radiation photons. Those photons produce more pairs. Those pairs are accelerated and emit more photons. Those photons create still more pairs. It is a cascade, a runaway avalanche of particle creation. Each generation of particles produces the photons that create the next generation. Each stage amplifies the number of electrons and positrons flooding the magnetosphere. Within microseconds, staggering numbers of particles are manufactured from essentially nothing, conjured out of the electric and magnetic fields of the spinning neutron star. The energy to create all the particles does not come from some external source. It comes from the rotation of the pulsar itself. Every electron-positron pair that springs into existence represents a tiny fraction of the pulsar's rotational energy converted into the mass and motion of new particles. The flywheel is being drained, one pair at a time, billions upon billions of times per second. Let me make sure the sheer strangeness of this process is not lost in the technical description, because what is happening here has no parallel in everyday experience. Nowhere else in your life does empty space suddenly produce matter. You do not see electrons and positrons appearing out of thin air in your living room. The vacuum around you is calm, stable, uneventful. But the vacuum near the Crab pulsar is none of those things. The electromagnetic fields there are so extreme that they destabilize the vacuum itself. They inject enough energy into a tiny volume of apparently empty space that the space responds by producing particles. Real, physical particles with mass and charge that did not exist a moment earlier. This is not a metaphor. This is not a simplification for the sake of storytelling. This is what actually happens according to the most precisely tested theory in all of physics: quantum electrodynamics. The equations predict it. The experiments confirm it. And the Crab pulsar does it continuously, on a scale that dwarfs anything humans have ever achieved in a laboratory. The most powerful laser facilities on Earth have been trying for decades to produce electron-positron pairs from intense electromagnetic fields. As of now, they have barely managed to observe the effect under the most carefully controlled conditions. The Crab pulsar does it effortlessly, every microsecond, generating floods of matter and antimatter from the energy of its own spinning magnetic field, filling its magnetosphere with a dense plasma of freshly minted particles. Every single one of those particles represents a conversion. Energy from the pulsar's rotation has become mass. The spin has become matter. And that matter, once created, is immediately accelerated and flung outward, carrying the energy away from the neutron star and into the surrounding nebula. The pulsar is literally spending its own rotation to manufacture the particles that form its wind. It is turning spin into substance. This cascade is what fills the magnetosphere with the plasma it needs to function as an engine. Without pair production, the space around the pulsar would be nearly empty, starved of charged particles, unable to carry the currents necessary for energy extraction. With pair production, the magnetosphere is dense with electrons and positrons, all being created, accelerated, and flung outward, all drawing their energy from the spin of the dead star beneath them. And this is where the pulsar wind is born. The particles accelerated along the open magnetic field lines, those lines that pass through the light cylinder and stream outward into space, carry magnetic field with them as they flow. This outflow of relativistic particles and magnetic field is called the pulsar wind. It is a continuous, powerful, relentless stream of energy and matter flowing away from the neutron star, strongest along the equatorial plane and along the polar directions. The pulsar wind from the Crab pulsar is extraordinary in its properties. The particles within it travel at velocities so close to the speed of light that the difference is almost immeasurable. They move at more than 99.9999% of light speed. Their effective mass, boosted by relativistic effects, can be thousands or even millions of times greater than their rest mass. Individually, each particle carries enormous energy. Collectively, the wind carries a power output that dwarfs anything in its cosmic neighborhood. The rate at which the Crab pulsar pours energy into its wind is roughly 100,000 times the total luminosity of our sun. Think carefully about what that comparison means. Our sun is a nuclear furnace. It converts 600 million tons of hydrogen into helium every single second, producing enough light and heat to sustain all life on Earth across a distance of 150 million kilometers. The sun is an enormously powerful object by any standard humans can comprehend, and the Crab pulsar's wind carries 100,000 times more energy per second than all of that. 100,000 suns packed into the output of an object 20 kilometers across, not by burning fuel, not by consuming matter, purely by spinning. Now I need to emphasize something here, because it is easy to confuse the pulsar wind with something more familiar, and the distinction matters enormously. The pulsar wind is nothing like the solar wind. Our sun also produces a wind, a stream of charged particles flowing outward through the solar system. The solar wind consists primarily of protons and electrons, the ordinary building blocks of hydrogen expelled from the sun's hot outer atmosphere at speeds of roughly 400 to 800 kilometers per second. The solar wind is a real and important phenomenon. It shapes the tails of comets, pushing them so they always point away from the sun. It creates the auroras at Earth's poles, when its particles interact with our planet's magnetic field. It inflates a vast bubble called the heliosphere that shields the entire solar system from some of the harshest radiation in interstellar space. But the pulsar wind from the Crab is a fundamentally different phenomenon. The solar wind moves at a few hundred kilometers per second. The pulsar wind moves at effectively the speed of light, nearly 300,000 kilometers per second. The solar wind is made of ordinary protons and electrons, stripped from the sun's atmosphere by thermal energy. The pulsar wind is composed primarily of electron-positron pairs, matter and antimatter, created from pure energy through pair production cascades in the pulsar's magnetosphere. The solar wind is driven by the thermal pressure of the sun's corona, a hot outer atmosphere heated to millions of degrees. The pulsar wind is driven by the electromagnetic extraction of rotational energy from a spinning magnetized neutron star. These are not variations on the same theme. They are entirely different phenomena, driven by entirely different physics. The word wind is used for both, but the resemblance ends with the name. And this leads to one of the most important points in understanding the Crab Nebula. One worth stating as plainly as possible, because it is the foundation upon which everything else rests. The Crab Nebula is not glowing because of leftover heat from the supernova explosion. The explosion happened nearly 1,000 years ago. If the nebula were simply cooling debris, coasting on whatever energy the supernova deposited into it, it would be far dimmer than it is. Calculations showed this decades ago. The energy from the original explosion is entirely insufficient to explain what we observe. Something else is required. The Crab Nebula is not powered by nuclear fusion. There are no fusion reactions occurring anywhere in the system. The neutron star is compressed far beyond any state where nuclear burning could contribute meaningful energy. Its interior consists of degenerate neutrons, not fusible fuel. The Crab Nebula is not powered by accretion. There is no disk of material. There is no companion star. Nothing is falling onto the neutron star and releasing gravitational energy. The pulsar sits alone. The Crab Nebula is powered by the spin of the pulsar. Rotational kinetic energy, extracted through the interaction of rapid rotation and an intense magnetic field, converted into electric fields that create and accelerate particles, channeled outward along open magnetic field lines as a relativistic wind of electrons, positrons, and embedded magnetic field. That wind carries roughly 100,000 times the luminosity of our sun, flowing continuously, relentlessly, pouring energy into the surrounding nebula every second of every day for nearly 1,000 years. The Crab pulsar is a cosmic generator, a dead star still at work, not because anything is feeding it, but because it was born spinning so fast and magnetized so intensely that the physics of electromagnetism would not allow it to sit there quietly. This spinning magnetic field generates electric fields. The electric fields create particles from the vacuum. The particles carry energy outward as a relativistic wind. The wind races away from the pulsar at nearly the speed of light, carrying with it the rotational energy of the dead star, converting the spin of a corpse into the glow of a nebula. This mechanism is elegant in its physics and staggering in its power. It runs without fuel, without combustion, without any of the processes that power every ordinary luminous object in the universe. It runs on spin, pure rotational energy, the last inheritance of a dead star, spent slowly over millennia as the neutron star gradually, imperceptibly decelerates. But the energy does not simply vanish into the nebula like water soaking into sand. The pulsar wind, carrying all that power, races outward at nearly the speed of light, and eventually it encounters something. The slowly moving shell of debris from the original supernova explosion is still out there, still expanding outward at a few thousand kilometers per second, still filling a vast volume of space around the pulsar. And when the relativistic wind, moving at nearly the speed of light, slams into that much slower wall of gas and debris, something violent and beautiful happens. A boundary forms, a shock, a place where the wind abruptly stops, where its kinetic energy is transformed into something else entirely, and everything downstream of that shock begins to glow in ways that astronomers can see, photograph, and study across every wavelength of light that telescopes can detect. The pulsar wind races outward from the Crab pulsar at nearly the speed of light, a flood of electrons, positrons, and magnetic field, carrying roughly 100,000 times the luminosity of our sun, streaming in all directions through the space surrounding the dead star. If nothing stood in its way, this wind would simply expand forever, thinning and weakening as it spread into the immensity of interstellar space, its energy diluted across an ever-growing volume until it became undetectable. But something does stand in its way, and that something is the wreckage of the very explosion that created the pulsar in the first place. When the progenitor star exploded in the year 1054, it flung its outer layers into space at speeds of several thousand kilometers per second. That material, the shattered remains of a massive star, has been expanding outward ever since. Nearly 1,000 years later, this debris cloud has grown to an enormous size, roughly 11 light years across. A vast, irregular shell of gas and dust, laced with heavy elements, forged inside the star during its lifetime and during the explosion itself. The cloud contains filaments of hydrogen, helium, carbon, oxygen, and heavier elements, all tangled together in a complex web of glowing gas. This is the visible structure of the Crab Nebula, the thing you see in those spectacular photographs. A chaotic, filamentary cloud of supernova debris, still expanding, still moving outward at roughly 1,500 kilometers per second. But this expanding shell is moving slowly compared to the pulsar wind. 1,500 kilometers per second is extraordinarily fast by any human standard. It would carry you from Earth to the Moon in about 4 minutes. But the pulsar wind moves at nearly 300,000 kilometers per second, the speed of light. The wind is roughly 200 times faster than the debris shell. And when something moving at nearly the speed of light encounters something moving 200 times more slowly, the collision is violent. This collision creates one of the most important structures in the entire Crab Nebula. It's called the termination shock. The termination shock is the boundary where the pulsar wind abruptly decelerates. Before this boundary, the wind flows freely, a relativistic river of particles and magnetic field streaming outward from the pulsar. Beyond this boundary, the wind has been stopped. Its bulk kinetic energy, the energy of all those particles moving at nearly the speed of light, is suddenly and violently converted into other forms of energy. Random particle motion, intensified magnetic fields, turbulence. The ordered, directed flow of the wind is transformed into a chaotic, energized mess of particles and fields swirling behind the shock front. Think of it as a cosmic traffic jam at the speed of light. The pulsar is continuously injecting new wind into the space around it. pushing particles outward at relativistic speeds. But those particles cannot push through the wall of supernova debris easily. The debris is dense and massive, the accumulated remains of an entire stellar envelope. So the wind piles up. It forms a region of intensely heated, magnetically turbulent plasma between the pulsar and the inner edge of the debris shell. And the boundary between the freely flowing wind and this piled up region is the termination shock. For the Crab Nebula, the termination shock sits roughly 1/3 of a light year from the pulsar. That is about 3 trillion kilometers, a distance that sounds enormous by everyday standards, but is actually quite small compared to the overall size of the nebula. The shock is deep inside the crab, relatively close to the central engine, forming a compact boundary that marks the place where the wind's journey ends and the nebula's glow begins. The conditions at this boundary are extreme even by the standards of high-energy astrophysics. Consider what is happening at the termination shock from the perspective of a single electron in the pulsar wind. That electron has been accelerated to within a hair's breadth of the speed of light. Its effective mass, boosted by relativistic effects, may be thousands of times its rest mass. It is hurtling outward from the pulsar as part of a continuous flood of particles and magnetic field, moving at nearly 300,000 kilometers per second. And then, in an instant, it hits the shock. The deceleration is not gentle. It is not gradual. The particle goes from a directed, ordered flow at nearly the speed of light to a chaotic, randomly oriented motion in a region of tangled, compressed magnetic field. The kinetic energy it carried as part of the wind does not vanish. It is redistributed. Some of it goes into heating the particle itself, increasing its random motion. Some of it goes into amplifying the magnetic field, compressing and tangling the field lines into a dense, turbulent web. The result is a region just downstream of the shock that is extraordinarily hot, extraordinarily magnetized, and extraordinarily bright. The most intense emission from the Crab Nebula, particularly in X-rays, comes from this narrow region just behind the termination shock, where the freshly decelerated particles are at their most energetic and the magnetic fields are at their most intense. What happens at and beyond this shock is what makes the Crab Nebula shine, because the particles that cross the termination shock do not simply stop moving. They're still extraordinarily energetic. The shock has converted their directed motion into random motion, scattering them in all directions, tangling them in amplified magnetic fields. These particles, electrons and positrons moving at nearly the speed of light, are now trapped in a region of intense magnetic field that fills the interior of the nebula. And when fast-moving charged particles encounter magnetic fields, they do something beautiful. They radiate. This radiation is called synchrotron radiation, and it is the single mechanism responsible for almost all of the light the Crab Nebula produces. Understanding synchrotron radiation is the key to understanding why the crab glows the way it does, across every wavelength of light, from the lowest energy radio waves to the highest energy gamma rays. The physics behind synchrotron radiation is straightforward in principle, though extreme in application. When a charged particle, an electron or a positron, moves through a magnetic field, the field exerts a force on the particle that pushes it sideways, perpendicular to its direction of motion. This force does not speed the particle up or slow it down. It curves its path. The particle spirals around the magnetic field line, tracing a helical corkscrew trajectory as it moves through space. It is like a bead threaded on a wire, except the wire is an invisible magnetic field line, and the bead is an electron moving at nearly the speed of light. Now here is the crucial point. Anytime a charged particle is accelerated, and following a curved path counts as acceleration, even if the speed does not change because the direction is changing, it emits electromagnetic radiation. For particles moving at ordinary speeds, this radiation is negligible. You do not notice your electrons glowing when current flows through a wire in your house. But for particles moving at relativistic speeds very close to the speed of light, the radiation becomes intense. The faster the particle moves, the more energy it radiates. The stronger the magnetic field forcing it to curve, the more energy it radiates. And at the speeds and field strengths found inside the Crab Nebula, the radiation is powerful enough to be detected across billions of kilometers of space. The energy of the emitted radiation depends on how fast the particle is moving and how strong the magnetic field is. Higher energy particles spiraling in stronger fields emit higher energy radiation. This is why the Crab Nebula glows across such an extraordinary range of wavelengths. The particles injected by the pulsar wind span an enormous range of energies. The most energetic electrons and positrons, the ones moving closest to the speed of light, emit X-rays and gamma rays. Moderately energetic particles produce visible light and ultraviolet radiation. Less energetic particles generate infrared and radio waves. The same basic mechanism, charged particles spiraling in magnetic fields, produces all of it. The only difference is the energy of the particles involved. And this is what gives the Crab Nebula its characteristic glow. When you look at a photograph of the crab taken in visible light, you see a ghostly, bluish-white glow filling the interior of the nebula, overlaid with reddish filaments of gas. The blue-white glow is synchrotron radiation. It is produced by relativistic electrons and positrons spiraling through the magnetic field that permeates the nebula's interior, radiating visible light as they go. The reddish filaments are something different. They are the actual supernova ejector. The filaments of gas blasted outward by the original explosion, glowing because they are heated and ionized. But the distinctive interior glow, the smooth, pale luminescence that fills the space inside those filaments, is pure synchrotron emission. And this is where an important clarification becomes necessary. Because there is a common misconception about how the Crab pulsar lights up its nebula, and it needs to be addressed directly. The pulsar does not illuminate the nebula the way a flashlight illuminates a room. The lighthouse beams that sweep around as the pulsar rotates do produce intense, concentrated radiation. But those beams are narrow. They sweep through a tiny fraction of the sky with each rotation. They do not bathe the entire nebula in light the way a light bulb illuminates a lampshade. If the beams were the only source of energy, only a tiny sliver of the nebula would be lit at any given moment, and the vast majority of the cloud would be dark. Instead, the nebula is lit from within by the particles that the pulsar wind has distributed throughout its interior. The wind carries particles outward. They cross the termination shock. They are scattered and trapped in the magnetic field that pervades the nebula. And then they radiate synchrotron emission in all directions from wherever they happen to be. The glow comes from everywhere inside the nebula simultaneously. It is not a beam sweeping through the dark. It is a diffuse, continuous emission from trillions upon trillions of particles scattered throughout a vast volume, each one individually spiraling around a magnetic field line and individually emitting radiation. The nebula glows from the inside out, powered by particles injected by the wind, but emitting from their own distributed locations throughout the remnant. The Crab Nebula is essentially a giant cloud of relativistic particles and magnetic field, energized by a central engine radiating synchrotron emission across the electromagnetic spectrum. And it is doing this right now as you listen to these words. Not as a fossil glow left over from some ancient event, as an active, ongoing process driven in real time by the energy of the Crab pulsar's rotation. This makes the Crab Nebula a type of object astronomers call a pulsar wind nebula. It is a cloud of relativistic particles and magnetic field, inflated and sustained by the wind from a central pulsar. There are other pulsar wind nebulae in the galaxy, but the Crab is by far the brightest, the best studied, and the most spectacular. It is the gold standard against which all others are measured. And one of the reasons it is so exceptional is that we can actually watch it change. Most astronomical objects appear static from a human perspective. Stars look the same year after year. Galaxies hold their shapes for millions of years. Even most nebulae evolve so slowly that 1,000 years of human observation would not reveal any visible change. But the Crab Nebula is different. The structures near the Crab pulsar, the features created by the ongoing interaction between the wind and the surrounding material, change visibly over weeks and months. The Hubble Space Telescope and the Chandra X-ray Observatory have been observing the Crab for decades. The images they have returned reveal a dynamic, evolving landscape of energy and light surrounding the central pulsar. These structures are not abstract features visible only in processed data. They are vivid, dramatic formations that shift and change on timescales, short enough for astronomers to watch them evolve. The most prominent inner structure is a bright ring, sometimes called the inner ring or the Taurus, surrounding the pulsar in the equatorial plane. This ring sits at roughly the location of the termination shock, where the pulsar wind is meeting the surrounding material and decelerating. The ring is bright in both visible light and X-rays because the freshly shocked particles are at their most energetic here. They have just crossed the shock boundary. Their energy has just been converted from directed bulk motion into random high-speed spiraling, and they are radiating fiercely. The ring is not smooth and uniform, it has structure. Bright knots and arcs appear within it, intensity variations that come and go over weeks and months. Some knots brighten dramatically and then fade. Others appear to move outward from the ring, carried by the flow of particles into the broader nebula. The ring itself pulses and shifts in brightness, reflecting variations in the pulsar wind's power output, or changes in the interaction between the wind and the surrounding medium. Extending outward from the ring, astronomers observe features called wisps. These are bright, narrow arcs of emission that appear near the pulsar, move outward at apparent speeds that can reach half the speed of light, and then fade as they expand into the larger nebula. The wisps are thought to be waves or instabilities in the shocked wind, ripples in the outflow that brighten as they compress the magnetic field and particles, then dim as they spread out. Watching these wisps is like watching waves radiating outward from a stone dropped into a pond, except the pond is made of relativistic plasma, and the waves are moving at a significant fraction of a light speed. Hubble has captured time-lapse sequences of these wisps that are genuinely breathtaking. Frame by frame, you can see bright arcs appear near the pulsar, sweep outward, distort, interact with other features, and eventually dissolve into the general glow of the nebula. It is one of the few places in astronomy where you can watch a cosmic engine at work in something approaching real time. Most of the universe changes too slowly for human eyes to detect. The Crab changes fast enough for telescopes to capture in months what would normally take millennia. Some of these wisps have been tracked moving outward at speeds exceeding half the speed of light. Consider what that means in practical terms. A feature the size of our entire solar system appears near the pulsar, brightens until it becomes one of the most luminous structures in the inner nebula, and then races outward at 150,000 kilometers per second, distorting and fading as it goes. The entire life cycle of such a wisp, from first appearance to final dissolution, can unfold over just a few months. Astronomers have assembled these sequences into movies that compress a year of cosmic activity into a few seconds of footage. Watching them is unlike anything else in observational astronomy. You're watching energy flow. You're watching the pulsar's power made visible, stamped into the plasma and carried outward like ripples from a stone thrown into still water, except the stone is a neutron star, and the water is a sea of matter and antimatter moving at relativistic speed. Each wisp represents a pulse of energy that originated in the spin of the dead star, passed through the magnetosphere, crossed the termination shock, and emerged as a visible, moving structure that human telescopes can track and record. Along the rotation axis of the pulsar, perpendicular to the equatorial ring, two narrow beams of emission extend outward in opposite directions. These are the polar jets, collimated outflows of particles and magnetic field that shoot away from the pulsar along the spin axis. The jets extend for roughly a light year in each direction, punching through the surrounding nebula like needles through fabric. The jets are also dynamic. Chandra X-ray images show knots and bends in the jets that change position over time. Material appears to flow along the jets at high speed, with bright blobs moving outward and occasionally appearing to change direction or interact with surrounding structures. The jets are not perfectly straight or perfectly stable. They wobble slightly, possibly because of precession of the pulsar's spin axis or instabilities in the flow. Like the wisps, the jets are evidence of the pulsar's continuing activity, visible markers of the energy still flowing outward from the central engine. The combined picture, the equatorial ring, the expanding wisps, the polar jets, is a portrait of a dead star still actively shaping its environment. The pulsar is not a passive object sitting inside a glowing cloud. It is the architect of the structures within the cloud. Every bright ring, every moving wisp, every jet is a direct consequence of rotational energy being extracted from the neutron star and pumped into the surrounding space. The Crab Nebula is not a relic. It is a machine in motion. Now let us consider the broader structure. Beyond the inner ring and the wisps, beyond the immediate environment of the pulsar, lies the bulk of the Crab Nebula itself. This is the vast cloud of material that appears in wide-field photographs as a tangle of glowing filaments embedded in a smooth, blue-white glow. This larger structure spans roughly 11 light-years across and contains material totaling several solar masses, all of it debris from the original supernova explosion. The filamentary structures, those twisted ropes and sheets of glowing gas visible in optical photographs, are primarily composed of the heavy elements synthesized inside the progenitor star and during the explosion itself. Hydrogen, helium, carbon, nitrogen, oxygen, neon, sulfur, and other elements are all present, compressed into dense threads and clumps by the interaction between the expanding ejector and the pressure exerted by the pulsar wind nebula from within. From the inside, the relativistic plasma inflated by the pulsar wind pushes outward against the inner surface of the ejector shell. This pressure sweeps the ejector outward, compresses it, and sculpts it into the filamentary structures we observe. The filaments glow partly because they are heated by the surrounding radiation field, and partly because of their own atomic emission processes. When atoms in the filaments are excited by ultraviolet radiation, or by collisions with energetic particles, they emit light at specific wavelengths characteristic of each element. The red and orange hues, visible in many photographs of the crab, come from hydrogen and nitrogen emission in these filaments, in contrast to the blue-white synchrotron glow filling the spaces between them. So the Crab Nebula is really two things layered on top of each other. One is a shell of supernova debris, the remnant of the original explosion, made of ordinary matter rich in heavy elements, glowing through atomic emission processes. The other is a bubble of relativistic plasma and magnetic field blown by the pulsar wind, filling the interior of the debris shell, glowing through synchrotron radiation. The two components interact. The wind-driven bubble pushes on the filaments from the inside. The filaments confine the bubble, preventing it from expanding freely. It is a dynamic equilibrium, constantly adjusting as the pulsar continues to inject energy and the debris continues to expand. This layered structure is visible across the electromagnetic spectrum. In radio waves, astronomers see the synchrotron emission from the lowest energy particles, producing a smooth glow that fills the interior of the nebula. In infrared, they detect thermal emission from dust grains mixed into the ejector filaments. Dust that was either created in the supernova explosion or condensed in the cooling debris afterward. The amount of dust in the crab is surprisingly large, estimated at roughly 1/4 to 1/2 of a solar mass. This discovery was significant because it demonstrated that supernovae can be prolific dust factories, manufacturing substantial quantities of solid particles from the heavy elements forged during the explosion and its aftermath. As atoms of carbon, silicon, oxygen, and iron cool in the expanding ejector, they bond together into tiny solid grains, each one smaller than a wavelength of visible light. These grains absorb higher energy radiation from the surrounding synchrotron glow, warm up, and re-emit that energy as infrared light. In infrared images of the crab, this dust emission traces the densest filaments, revealing structures that are sometimes invisible or faint at other wavelengths. In visible light, both the synchrotron glow and the filamentary atomic emission are visible, producing those iconic images of blue-white light laced with red filaments. In ultraviolet, the synchrotron component dominates, since the filaments are less prominent at these shorter wavelengths. In X-rays, only the highest energy synchrotron emission is visible, concentrated near the pulsar where the particles are freshest and most energetic. And in gamma rays, the very highest energy particles produce emission that extends to photon energies far beyond what any human technology can generate. The Crab Nebula has been detected at photon energies exceeding 100 trillion electron volts. These are among the highest energy photons ever detected from any source in the sky. They are produced by electrons and positrons moving so close to the speed of light that their effective mass has been boosted by factors of tens of millions. Even by the extreme standards of high-energy astrophysics, the Crab is exceptional. It produces radiation across a range of energies spanning more than 20 orders of magnitude, from radio wavelengths measured in meters to gamma rays with wavelengths smaller than an atomic nucleus. A single object, powered by a single mechanism, producing emission across this extraordinary range of the electromagnetic spectrum. This is why the Crab Nebula has been called the Rosetta Stone of astrophysics. It was through studying the Crab that astronomers first confirmed the connection between pulsars and supernova remnants. It was through the Crab that they confirmed that pulsar wind nebulae are powered by rotational energy. It was through the Crab that they developed and tested theories of synchrotron radiation in cosmic environments. It was through the Crab that they first observed the dynamic, evolving structures produced by pulsar winds interacting with supernova ejecta. And it is the Crab that continues to serve as the primary testing ground for every new theory about how dead stars inject energy into their surroundings. Part of what makes the Crab so invaluable is its proximity. At roughly 6,500 light-years from Earth, it is close enough that modern telescopes can resolve detailed structures within it. The inner ring is visible. The wisps are visible. The jets are visible. Individual filaments in the ejecta can be studied spectroscopically to determine their chemical composition and velocity. Astronomers can measure the expansion of the outer shell by comparing images taken decades apart. Watching the filaments move outward in real time, they can track the wisps and jets through sequences of images taken months or years apart, assembling time-lapse movies of a cosmic engine at work. There are other pulsar wind nebulae in the galaxy. The Vela pulsar, about 1,000 light-years away, powers its own wind nebula. There are dozens of others at various distances, but none of them are as bright, as well-resolved, or as thoroughly studied as the Crab. The Crab occupies a unique position in astronomy. It is the brightest and best-studied example of a dead star actively powering its surroundings, visible across every wavelength, changing on human timescales, accessible to every major telescope facility on Earth and in space. The Crab Nebula is also one of the brightest persistent sources of high-energy radiation in the sky. For decades, astronomers used the Crab as a standard reference source for calibrating X-ray and gamma-ray instruments. Its intensity was considered so constant and so well characterized that other sources were measured in units called crabs, with 1 crab equal to the flux of the Crab Nebula. A source half as bright as the Crab was rated at half a crab. A source 10 times brighter was 10 crabs. The Crab was the yardstick. Then, in 2010 and 2011, astronomers detected something unexpected. Powerful gamma-ray flares from the Crab Nebula. Brief bursts of extremely high-energy radiation, lasting days, during which the nebula's gamma-ray output increased by several times its normal level. These flares were a surprise. The Crab's synchrotron emission had been considered stable. The discovery of flares showed that the nebula's inner regions, near the termination shock and the pulsar wind, are more dynamic and more violent than previously understood. Something, probably magnetic reconnection events in the turbulent plasma near the shock, was accelerating particles to even higher energies than the steady-state wind normally produces, creating brief surges of gamma-ray emission. The flares were powerful enough to force astronomers to reconsider the Crab's role as a calibration standard. For decades, the unit of measurement called a crab had rested on the assumption that the Crab Nebula's high energy output was essentially constant. The discovery that it could surge by factors of several within days undermined that assumption. The yardstick itself was flexing. This was unsettling in a productive way because it revealed physics that steady-state models of the nebula had not predicted. The leading explanation involves magnetic reconnection, a process in which tangled magnetic field lines near the termination shock suddenly snap and reconfigure, releasing stored magnetic energy in a violent burst. The energy released in a reconnection event is converted almost instantly into the acceleration of nearby particles, boosting them to energies far beyond what the normal wind produces. These ultra-energetic particles radiate gamma rays so intense that even instruments orbiting Earth can detect the surge from 6,500 light-years away. The flares typically last a few days before subsiding, as the temporarily disrupted magnetic field relaxes back into a more stable configuration, and the burst of extra energetic particles radiates away its energy. Then, the nebula settles back to its usual brightness, the steady engine reasserting itself until the next reconnection event builds enough magnetic tension to snap again. These flares reinforce the picture of the Crab as a living, evolving system. Not a static remnant passively cooling down, but an active engine capable of sudden, dramatic releases of energy. The pulsar at the center keeps pumping. The wind keeps flowing. The shock keeps processing particles. And occasionally the system produces bursts of energy that remind us just how much power is continuously being channeled through this relatively small corner of space. All of this, the glow, the wisps, the jets, the ring, the flares, the emissions spanning 20 orders of magnitude in photon energy, all of it traces back to the same source. A neutron star 20 kilometers across, spinning 30 times a second, pouring rotational energy into the surrounding space through the interaction of its rotation and its magnetic field. The mechanism is the same one we explored earlier. Spin and magnetism create electric fields. Electric fields create particles. Particles form a wind. The wind hits the debris. The particles radiate. The nebula glows. Every photon of synchrotron light that leaves the Crab Nebula and travels 6,500 light-years to reach a telescope on Earth carries a tiny fraction of the Crab pulsar's rotational energy. When that photon strikes a detector and is recorded as data, we are capturing energy that originated in the spin of a dead star. Energy that was extracted through electromagnetic forces, converted into the motion of particles, carried outward by the wind, randomized at the shock, and finally emitted as radiation. The chain of energy transfer is long and intricate, but it is unbroken. From the spin of a city-sized neutron star to a photon landing on a sensor, every link connects back to the same source. And this means the Crab Nebula is more than just a pretty object in the sky. It is a visible, ongoing demonstration of how the universe converts one form of energy into another. Rotational kinetic energy into electromagnetic energy. Electromagnetic energy into particle kinetic energy. Particle kinetic energy into synchrotron radiation. Each conversion obeys the laws of physics precisely, operating continuously, day and night, year after year, century after century. But nothing lasts forever. The engine at the center of the Crab is powerful, but it is not infinite. Every photon that leaves the nebula, every particle accelerated by the wind, every erg of synchrotron radiation emitted from the twisted magnetic fields. All of it comes at a cost, and that cost is paid by the Crab pulsar's rotation. The flywheel is being drained, the spin is slowing, and as it slows, the power output decreases. The wind weakens, the nebula dims. Slowly, imperceptibly from one human lifetime to the next, but inevitably, relentlessly, the Crab is running down. The dead star is still powering its nebula tonight, but it will not do so forever. And understanding how and why it slows, and what will eventually happen when the engine finally grows too weak to sustain the glow, is the final stage in this extraordinary story. Every second that the Crab pulsar pumps energy into its surrounding nebula, every particle it accelerates, every photon of synchrotron radiation that streams away into space comes at a price, and that price is paid by the pulsar's own rotation. This is the inescapable bargain at the heart of the entire system. The Crab pulsar's energy source is its spin. There is no external fuel supply, no fusion reactor, no infalling material. The only reservoir of energy available is the rotational kinetic energy stored in the neutron star's enormous mass, spinning at 30 revolutions per second. And every time the pulsar extracts a fraction of that rotational energy and converts it into wind, radiation, and accelerated particles, the spin rate must decrease. The flywheel must slow down. There is no alternative. Energy is conserved. You cannot spend energy without the account balance dropping, and we can measure this slowdown directly. The Crab pulsar's rotation period, the time it takes to complete one full revolution, is increasing, not by a large amount, not by anything you could perceive without extraordinarily precise instruments, but by a measurable, consistent, relentless amount. Every single day, the Crab pulsar's rotation period grows longer by roughly 38 nanoseconds, 38 billionths of a second, an interval so short that no human sense could detect it. An interval that, in everyday terms, is completely insignificant, but accumulated over days and weeks and months and years and centuries, it adds up. 38 nanoseconds per day means roughly 14 microseconds per year. Over a century, the period increases by about 1.5 milliseconds. Over 1,000 years, by about 15 milliseconds. The Crab pulsar today spins slightly more slowly than it did when Chinese astronomers recorded the guest star in 1054. Back then, freshly formed in the violence of the supernova, it was spinning even faster than it does now. Astronomers estimate that its initial rotation rate may have been roughly 60 revolutions per second, twice its current rate. Nearly 1,000 years of continuous energy output have drained enough rotational energy to cut the spin rate nearly in half. And this measured slowdown is not just a curiosity, it is the key piece of evidence that connects the pulsar to the nebula's glow. Because when you calculate how much rotational energy the pulsar is losing based on its measured deceleration, and then compare that number to the total observed luminosity of the Crab Nebula across all wavelengths, from radio to gamma rays, the two numbers match. This agreement is remarkable. The rate at which the Crab pulsar loses rotational energy, a quantity physicists call the spin-down luminosity, is approximately 5 × 10⁻31 watts. That is roughly 100,000 times the total luminosity of our Sun. And the total energy radiated by the Crab Nebula across the electromagnetic spectrum is approximately the same number. The energy coming out of the nebula matches the energy being lost by the pulsar's rotation. The accounts balance. This was the decisive evidence that settled the question of what powers the Crab Nebula. When astronomers first proposed that the pulsar's rotational energy could be the engine, some were skeptical. It seemed almost too simple. A spinning ball of neutrons, 20 kilometers across, powering an 11 light-year nebula just by slowing down. But the numbers do not lie. The spin-down luminosity matches the observed luminosity. Every watt of power radiated by the nebula can be accounted for by the loss of rotational energy from the central pulsar. The energy budget closes perfectly. This also means we can predict the future. Because the pulsar is losing rotational energy at a known rate, and we know how much energy is left in the spin, we can estimate how long the engine will continue to run and how the nebula will change as the engine gradually weakens. But before we look at that future, there is one more aspect of the pulsar's behavior that deserves attention, because it reveals something about the internal structure of the neutron star itself. Every measurement of the Crab pulsar's spin confirms that it is slowing down steadily. The deceleration is smooth and predictable, following a mathematical relationship that allows astronomers to forecast the pulsar's rotation rate years or even decades into the future with extraordinary accuracy. But occasionally, without warning, the smooth slowdown is interrupted by a sudden, tiny anomaly. The pulsar abruptly speeds up. These events are called glitches. They are sudden, small increases in the pulsar's rotation rate, jumps that happen in less than a second, and then gradually relax over days or weeks as the pulsar settles back toward its normal spin-down behavior. The Crab pulsar experiences glitches roughly once every few years. Though the timing is not perfectly regular, each glitch increases the spin rate by a tiny fraction, typically a few parts per billion. These are not large events by any external measure. They do not noticeably change the pulsar's appearance or the nebula's brightness, but they are detectable with precise timing instruments, and they tell us something important about what is happening inside the neutron star. The leading explanation for pulsar glitches involves the interior structure of the neutron star. Beneath the thin outer crust, a rigid lattice of crystallized nuclei perhaps a kilometer thick, the interior of a neutron star contains a vast sea of neutrons in a superfluid state. Superfluids have a remarkable property. They can flow without any friction whatsoever. And because they have no friction, a superfluid can rotate independently of the container that holds it. In a neutron star, this means the superfluid interior can spin at a slightly different rate than the solid crust. As the pulsar slows down, the crust decelerates because it is directly coupled to the magnetic field, which is doing the work of energy extraction. But the superfluid interior, frictionless and detached, does not slow down at the same rate. It retains its angular momentum, spinning slightly faster than the crust. Over time, a difference builds up between the rotation rate of the crust and the rotation rate of the superfluid interior. The interior is spinning faster. The crust is spinning slower. Angular momentum is stored in the differential rotation. Then, suddenly, something gives. A mechanism that is still not fully understood, possibly involving the unpinning of quantized vortices in the superfluid, causes a rapid transfer of angular momentum from the faster spinning interior to the slower spinning crust. The crust suddenly speeds up by a tiny amount, absorbing angular momentum from the interior. That is the glitch. The spin rate of the crust jumps upward, and then over the following days and weeks, the system gradually relaxes as the crust and interior recouple, and resume their slow, steady deceleration together. Glitches are fascinating because they give us an indirect way to probe the interior of a neutron star, a place that is completely inaccessible to direct observation. We cannot see inside a neutron star. We cannot send a probe there. The only way to learn about the conditions inside, the superfluid behavior, the density profile, the exotic states of matter that may exist in the innermost core, is through their external signatures. Glitches are one of those signatures. By measuring how large the glitches are, how often they occur, and how long the recovery takes, physicists can constrain models of the neutron star's internal structure, testing theories about superfluidity at nuclear density against real observational data. But glitches are a secondary story in the larger narrative of the Crab Nebula. They are brief interruptions in an otherwise smooth and relentless process. The overwhelmingly dominant behavior of the Crab pulsar is simple. It is slowing down, losing rotational energy, transferring that energy into its surroundings through the mechanism of the pulsar wind. And this process will continue for a very long time, but it will not continue forever. And the long-term future of the Crab Nebula is written in the physics of the spin down itself. As the pulsar slows, the rate at which it loses energy decreases. This is not immediately obvious, so let me explain why. The power output of a rotating magnetic dipole, which is the basic model for how a pulsar radiates energy, depends on the fourth power of the rotation rate. If the spin rate drops by half, the power output drops by a factor of 16. If it drops by a factor of 3, the power output drops by a factor of 81. The relationship is steep. A modest decrease in spin rate produces a dramatic decrease in power. This means the Crab pulsar was far more powerful in the past than it is today. When it was born, spinning perhaps 60 times per second, its power output was roughly 16 times higher than its current output. Because the spin rate was about twice what it is now, and power scales as the fourth power. In those early centuries, the pulsar was flooding its nebula with energy at a prodigious rate, inflating the synchrotron bubble rapidly, driving the ejector outward with tremendous force. And it means the Crab pulsar will be far less powerful in the future. As the spin continues to slow, the power output will continue to drop, and the drop will accelerate. The pulsar's energy budget is not being depleted at a constant rate. It is being depleted at a rate that decreases over time, because the slower it spins, the less efficiently the electromagnetic extraction process operates. The engine winds down, and as it winds down, it loses the ability to sustain the same level of output. Over the next several thousand years, the changes will be subtle. The Crab Nebula will remain visible and impressive. The synchrotron emission will persist. The wisps and jets will continue to dance near the pulsar. An astronomer observing the Crab 5,000 years from now would still recognize it as a spectacular object, but it will be dimmer. The total luminosity will have decreased by a measurable amount. The wind will carry less energy. The termination shock will sit closer to the pulsar because the weaker wind cannot push as far against the surrounding ejector. The inner structures will be smaller and less dramatic. Over tens of thousands of years, the changes become more pronounced. And here is where the different wavelengths of light begin to tell different stories. Because synchrotron radiation has a crucial property. The highest energy particles, the ones responsible for the highest energy radiation, lose their energy the fastest when a relativistic electron spirals in a magnetic field and emits synchrotron radiation The energy it radiates comes from its own kinetic energy. The particle is literally spending its own energy to produce light. And the rate at which it loses energy depends on how fast it is moving and how strong the magnetic field is. The most energetic particles, the ones producing X-rays and gamma rays, radiate so intensely that they burn through their energy in a relatively short time. A particle energetic enough to produce X-ray synchrotron emission in the Crab's magnetic field may exhaust its energy in just a few decades or centuries. To maintain X-ray emission, the pulsar must continuously inject fresh high-energy particles through the wind. If the wind weakens, the supply of fresh high-energy particles drops, and the X-ray emission fades because the existing particles burn out faster than they are replaced. Lower energy particles, the ones producing visible light and radio waves, lose energy much more slowly. A particle producing visible synchrotron emission might take thousands of years to radiate away its energy. A particle producing radio waves might take millions of years. These particles persist in the nebula long after they were injected, continuing to radiate long after the wind that created them has weakened. This means the Crab Nebula will not fade uniformly across all wavelengths. It will fade from the top down, starting with the highest energy radiation and working its way down to lower energies. X-rays will dim first, then ultraviolet, then visible light, then infrared, and finally, last of all, radio waves. The nebula will age in stages, like a dying fire that loses its blue flame first, then it's yellow, then it's orange, and finally glows only as dim red embers before going dark entirely. Tens of thousands of years from now, the Crab Nebula may have lost most of its X-ray emission. The inner ring and jets, which are bright primarily in X-rays produced by the freshest, most energetic particles, will have faded significantly. The wisps may be gone entirely, or reduced to faint shadows of their current brilliance. But the broader nebula may still glow in visible light and radio waves, sustained by the long-lived lower energy particles accumulated over centuries of wind activity. Hundreds of thousands of years from now, even the visible light emission will be fading. The synchrotron glows that currently gives the Crab its distinctive blue-white interior luminescence will weaken as the particles responsible for it gradually exhaust their energy, and the weakened wind fails to replace them at sufficient rates. The filamentary ejecta, still expanding outward, will have thinned considerably. The nebula will be larger but dimmer, a ghostly shell of dispersing gas with a fading glow at its center. The expanding ejecta will continue to interact with the surrounding interstellar medium. As the shell pushes into the thin gas between the stars, it will sweep up material, creating a new shock at its outer boundary. Over time, the swept-up interstellar material will exceed the mass of the original ejecta, and the expansion will decelerate. The filaments will fragment and blend into the surrounding gas. The sharp boundary of the nebula will blur. The coherent structure visible today will gradually dissolve into the general fabric of the interstellar medium, its material mixed into the gas and dust that fills the space between stars. Eventually, after millions of years, the Crab Nebula as a recognizable object will cease to exist. The ejecta will have merged with the interstellar medium. The synchrotron emission will have faded to undetectable levels even at radio wavelengths. The pulsar, by then spinning far more slowly, perhaps once every few seconds or even slower, will no longer generate a wind powerful enough to inflate any kind of visible nebula. It will still be there, still spinning, still possessing a magnetic field, still technically losing a rotational energy, but the rate of energy loss will be so small that no observable nebula will be sustained. The pulsar itself will persist for an extraordinarily long time. Neutron stars are fantastically durable objects. They do not burn out. They do not decay except on timescales so long they are essentially infinite by human reckoning. The Crab pulsar will continue to exist as a cooling neutron star, gradually radiating away its residual thermal heat over millions of years, slowly spinning down, its magnetic field possibly decaying over millions or billions of years through processes in its interior. Eventually it will become a cold, dark, slowly rotating ball of neutrons, drifting through the galaxy, still extraordinarily dense, still containing 1.5 times the mass of our Sun, still 20 kilometers across, but invisible, silent, no longer powering anything, no longer producing detectable pulses, a dead star that has finally finished its work. The heavy elements scattered by the supernova and dispersed by the pulsar wind into the interstellar medium will not go to waste. They will mix with the gas and dust between the stars, enriching the raw material from which future generations of stars and planets will form. The carbon, oxygen, silicon, iron, and other elements forged inside the Crab's progenitor star and scattered by its explosion are now part of the galaxy's chemical inventory. Billions of years from now, some of those atoms may find their way into a collapsing cloud of gas, becoming part of a new star, a new planetary system, perhaps even a new world where conditions allow complexity to emerge. The Crab Nebula is not just a tomb. It is also a seedbed. The death of one star provides the raw materials for the birth of others. This brings us back to where we started, to the contradiction that opened this entire story. The star is dead. It died nearly 1,000 years ago in one of the most violent events the universe routinely produces. Its nuclear furnace is extinguished. Its fuel is spent. Its outer layers were blown into space and have been expanding as a thinning cloud of debris ever since. By every ordinary measure, this should be the end of the story, but it is not the end, because the collapse that killed the star also created something new. A neutron star. A city-sized object so dense that a teaspoon of its material would weigh billions of tons. And that neutron star was born spinning, dozens of times per second, wrapped in a magnetic field trillions of times stronger than Earth's. These two properties, the spin and the magnetism, are not passive traits. They are active. They interact. The spinning magnetic field generates electric field powerful enough to create matter from energy, to fill the surrounding space with particles accelerated to nearly the speed of light. Those particles stream outward as a relativistic wind, carrying the rotational energy of the dead star into the surrounding debris. When the wind strikes the debris, the particles radiate. Synchrotron emission floods the nebula with light across every wavelength. The cloud glows, not from leftover heat, not from residual explosion energy, not from accretion or fusion, from the spin of a dead star. And so the Crab Nebula shines tonight, nearly 1,000 years after the explosion that created it. Powered entirely by the rotation of an object smaller than most cities on Earth, a neutron star 20 kilometers across, containing more mass than our Sun, spinning 30 times every second, converting its own rotation into the light that fills an 11 light-year cloud with energy. Slowly, imperceptibly, it decelerates. The flywheel drains, the engine weakens, but tonight, and for thousands of years to come, it is still running. There is something deeply remarkable about this. In a universe dominated by processes that are either instantaneous on cosmic timescales or unimaginably slow, the Crab Nebula exists in a rare middle ground. It changes fast enough for us to watch it evolve. The wisps move, the jets shift, the ring brightens and dims. Astronomers can assemble time-lapse sequences that compress months of observation into seconds of footage, watching structures the size of the solar system appear, move, and dissolve. This is almost unheard of in astronomy. Most cosmic objects change so slowly that 1,000 years of human observation would not reveal the slightest difference. But the Crab is alive with change, driven by an engine that operates on timescales accessible to human attention. The Crab is also a window into a broader truth about the universe. Dead stars are not passive objects. Throughout the Milky Way and beyond, neutron stars born in ancient supernovae continue to shape their surroundings. Pulsars inject energy into the interstellar medium. Pulsar winds carve bubbles in the gas between the stars. Relativistic particles from pulsar wind nebulae contribute to the cosmic ray population that fills the galaxy. The death of a massive star is not the end of its influence. It is the beginning of a new kind of influence, subtler than the original star, but remarkably persistent. The Crab Nebula is simply the best, the brightest, the closest example of this phenomenon. It is the place where we can see most clearly how a dead star continues to work, how rotational energy can be converted into radiation, how a neutron star's magnetic field and spin can produce phenomena as dramatic and beautiful as any living star, how the remnants of destruction can glow with an energy that seems, to human eyes, almost like life. And perhaps that is the most profound takeaway of all. In the universe, endings are rarely absolute. A star dies, but its corpse keeps working. An explosion flings debris across light years of space, but a tiny engine at the center keeps that debris glowing for millennia. Energy does not disappear. It transforms. The nuclear energy that powered the star for millions of years was converted into gravitational potential energy during the collapse, into kinetic energy of the supernova ejector, into rotational kinetic energy of the neutron star. And now, slowly, steadily, that rotational energy is being converted into the light that fills the Crab Nebula. Each conversion follows the laws of physics exactly. Each transfer is precise, accountable, measurable, nothing is wasted, nothing is lost. The energy simply changes form, passing from one state to another, from rotation to radiation, from a spinning dead star to a glowing cloud visible across 6,500 light-years of space. So the next time you look toward the constellation Taurus on a clear winter night, if you have a small telescope or even a good pair of binoculars, try to find the Crab Nebula. It is a faint, fuzzy patch of light near the tip of one of the bull's horns. It does not look like much through a small instrument, just a pale smudge against the darkness. But now you know what that smudge really is. You know that at its center sits a neutron star smaller than the city you live in, spinning 30 times a second, wrapped in a magnetic field powerful beyond comprehension. You know that this dead star is converting its own rotation into the energy that makes the nebula glow. You know that wisps and jets and rings of shocked plasma dance around it in a dynamic display that changes from month to month. You know that the engine is slowly winding down, the flywheel draining, the glow destined to fade over thousands and millions of years, and you know that the light entering your telescope tonight has traveled for 6,500 years to reach you. It left the Crab Nebula when human civilization was in its early chapters, long before the pyramids at Giza were built, when empires we now study in history books had not yet been imagined. That light has been crossing the darkness of interstellar space for all that time, carrying with it the energy of a dead star's rotation, a message written in synchrotron radiation and delivered across the galaxy. The star that once burned in the constellation Taurus is gone. It will never return. But its remnant, smaller than a city, denser than an atomic nucleus, spinning 30 times every single second, is still at work. Still powering a nebula visible across thousands of light years. Still teaching us how the universe transforms destruction into beauty. Still reminding us that in the cosmos, death is not always the final word. Tonight, the dead star still powers the Crab Nebula. And for now, that is enough.